Welcome to week 3 of Modern Geometry. In this week, we're going to take a look at classical triangle centers. For our first proof this week, we're going to use what we learned in chapter 0 to prove that we have two similar triangles and that AB is equal to 2ED. Now that might seem a little bit vague, but if you're in my class, then you're already working through these same types of experiences in GeoGebra. So in GeoGebra, what you have done, and this is for the benefit of you and anybody who's not in my class and just watching this video, what we have done in GeoGebra is we've created triangle ABC. We found all of those medians. And we have already proved that if we had a line that connected these two medians, that the larger triangle ABC would be similar to the smaller triangle, and we showed that just by looking at the corresponding angles. So we didn't do a proof of this yet, that's what we're going to do now, but we did show on GeoGebra that it was true. So what I want is, in my given statement, I want to say that I've got this triangle ABC, and we're going to use the same vertices that were given to us in GeoGebra that says let D be the side opposite A, and E be the side opposite B, and we're not going to even do F because obviously F is not one of the vertices that I need here. So for my given, I'm going to say let a triangle ABC be a triangle, and let E and D be the midpoints of side AC and BC respectively, and that's it for given. What am I trying to prove? I am trying to prove two things. First of all, that the triangles are similar. ABC is similar to EDC, and that AB is equal to 2ED. So before I get started, I want to draw our attention to Euclid's proposition VI.2, which we'll use quite often. And this one says if we have a triangle ABC and we have points on the sides of two of the sidelines, then DE is parallel to BC. So basically we're saying that we can show that this line and this line are parallel if we can show that the ratio of the smaller segment of the triangle to the larger segments, because obviously these are two separate triangles, is equal to the ratio of another side, smaller triangle to larger triangle. Now, why did I say it that way? Because if you'll notice, my vertices don't line up to the picture that I'm drawing, and that's okay. So even though it says D and E are midpoints of AB and AC, and obviously I used E as the midpoint of AC, and D is the midpoint of BC. So really I'm using BC here instead. You get the idea that it's still the same concept, and that's how we can use theorems. So I'm going to start my proof, and I'm going to be using Euclid's proposition, and I want you to notice that this is an if and only if, which means we can go in either direction. So if I can show that the ratios are equal, then I can say that the lines are parallel, or vice versa. So do I know that the lines are parallel? No. But by the midpoint theorem, I can say that AE is equal to EC, and that's what we're talking about measures, and BD is equal to DC. So by algebra, I can say that BC is equal to 2CD. So I'm saying that these two are equal. So the BC, the longer side, is equal to 2 of the smaller side. And I have to use CD or DC. That's important because this is the sideline of the smaller triangle. And in the same way, I can say that AC is equal to 2EC. Now, why is that important? Because I can say since DC over BC, so smaller to larger, is equal because that's in a 1 to 2 ratio. So 1 to 2, which is the same as EC over AC, then I can say that those two lines are parallel. So since I can say that's true by Euclid's proposition, VI2, the line AB is parallel to the line ED. Well, once I have parallel lines, I know lots of stuff that I can do. So what am I trying to prove? I'm trying to prove that the triangles are similar. And how do I prove that? I have to show that all of the angles are congruent. So I'm going to say, by the converse to corresponding angles theorem, and we use the converse when we already know we have parallel lines, then I'm going to say angle BAE is congruent to angle DEC, those are corresponding, and angle ABC right here is congruent to angle EDC. Now what? Well, since both triangles share angle C, I've essentially just proven that all of the angles are congruent. So triangle ABC is similar to triangle EDC, and that's just definition of similar triangles. Now, have I done everything that I need to do? No, I needed to show first that the two triangles were similar and that AB is equal to 2ED. So how am I going to do that? So how can I prove this? Well, I've already shown that AC is equal to 2EC. I can say since BC is equal to 2CD, this implies a 2-to-1 ratio for all corresponding sides. So essentially we're saying the sides, the two triangles are 2-to-1. So therefore I can say that AB is equal to 2ED. For our next proof, we are looking at a median coming from vertex A to the opposite sideline BC. And we are trying to prove that the line BE, now in your proof it's asking for H and K, but this is the way I already had this drawn and I didn't want to redo anything. Essentially, I'm trying to prove that BE is congruent to CF, which would be BH and CK on our actual proof. I'm also trying to prove that ABD, so the one I have drawn in purple, is congruent to ADC. So you can see how GeoGebra can be a helpful tool. No matter which way I turn this, those values are the same. So I can certainly show that in GeoGebra, but as we know, that's not a proof. However, this is a great way to begin a proof so that you understand what you are trying to prove before you start proving it. It's also a great way to do your diagram, so I can just take a screen grab of this and use that as my diagram for my proof. Now that we have an idea of what we're trying to prove and we can see that it is in fact true using GeoGebra, let's take a look at how to complete the proof. I've done a very poor rendering of my GeoGebra picture. I have triangle ABC. I've got D as the midpoint of BC. I have the feet of the perpendiculars H and K from B to C, from B and C to AD. So how am I going to get started? Let's get started with the given. So for given, I have let triangle ABC be a triangle, and let D be the midpoint of BC, and that's a segment. Now I'm not going to do the perpendiculars until I get to the proof. So what am I trying to prove? What to prove? That essentially I'm trying to prove that BH is equal to CK, and then it says conclude that the area of triangle ADB is equal to the area of triangle ADC. So I'm not even going to put this one in there because proving that will be a step on my way to proving that the two triangles are congruent. So let's take a look at how I can prove this. So for my proof, I'm going to start by drop a perpendicular, and I'm going to say both of them. So from B to and C to AD, but I'm going to say with feet H and K respectively. So we already know that D is the midpoint of BC, so I can say by definition of a midpoint, BD is equal to DC, which I've already marked, and I shouldn't have marked yet until I've actually said it. Now I can say since angle BHD and CKD, so BHD and CKD are right angles. And what reason do I have that? Because they're perpendicular lines, because obviously I just dropped a perpendicular, so that was the whole point. What can I say? I can say that BHD and CKD are congruent, of course, since they're both right angles. So angle CKD is congruent to angle BHD. So what I have so far is I have two triangles where I have an angle and a side, but I want to show that those two little triangles are congruent so that I can continue to show that BH is equal to CK, and then those triangles have equal areas and so forth. We know angle BDH is congruent to angle CDK. And now why do I know that? Because they are vertical angles. So vertical angle theorem. And now I have two triangles that are congruent by angle, angle, side. So by angle, angle, side, I can say that triangle BHD is congruent to triangle CKD. So why did I have to do all that? Because I'm first trying to prove that BH is equal to CK. So I can say that now because I have two triangles that are congruent. So by CPCTC, BH is equal to CK. I could obviously say BH is congruent to CK because that's what CPCTC says, but which implies, by definition of congruence, which you don't even have to write that, BH is equal to CK. So I've done half of that. What I'm trying to do now is conclude that the area of ABD, so let's take a look at ABD, this, well, I keep trying to change colors and it won't work. So nope, just stuck with white the whole time. You get the idea. So ABD is this part of the triangle. I'm trying to prove that that is the same as ADC, which is the right-hand side of the triangle, ADC. So how am I going to do that? Well, using our formula for area of a triangle, how am I going to find the area of triangle ABD, which is the one on the left? ABD is 1/2, and then base and height, which are of course perpendicular to one another. So the base and height have to be perpendicular. So in that figure, the perpendicular lengths are AD and BH. Okay, now the area of triangle, the other triangle, ADC, is equal to 1/2, again, base times height. So the base would be AD, and the height, which is at a 90-degree angle, and it doesn't matter that the end of the length is here, because this is where it makes the 90-degree angle, so that's CK. And now I can say since BH is equal to CK, we can substitute to write the area of triangle ADC is equal to 1/2 ADBH, which is the same as the area of triangle ADB. So therefore, the triangles are the same area.